In this video, I'm going to demonstrate how to use an oscilloscope to take some basic measurements. So let's do that now. Let's open up Multisim. I'm going to demonstrate it using the oscilloscopes that are in Multisim. So I've double-clicked on the icon that I have on my desktop, and hopefully Multisim is going to open up without any errors. And it'll come up to a workspace with a grid on it. Unless you've changed the properties or the default settings, this is the way that it will come up. You may have a box that pops up here on the left. You can exit out of that. The box here at the bottom, we could exit out of that and get rid of it, but it'll come back whenever we run the circuit or do something else. So I like to just leave it there. You can make it smaller so it's not so obtrusive to what we're doing. And I'm just going to build a simple circuit, something that we can easily look at on the oscilloscope and make a couple of measurements and just get used to using the oscilloscope. So some of this should be review for you guys, but hopefully it'll get you a little more comfortable in using the oscilloscopes here. So I'm going to build a simple circuit. I'm going to go to my power sources. I always select the ground first, and I'm going to place that here. And then I'm going to get an AC power source, which is basically a sine wave source. And let's see. And then I need a load resistor. I don't have to have one, but just so that we can complete a circuit or have a complete circuit, we're going to put something in here. And it could be a light bulb. It could be just about anything, but a resistor would be the simplest thing to put. I don't really care what the value is. So I've done placing my components. I'm going to right click on that. And now I'm going to build a little circuit. And I'm just clicking on the wires, dragging them so they look a little neater. Like so. And boom. All right, I have everything hooked up. And before I get too far, I'm going to save this. And I'm going to call it Oscilloscope Demo 1. And I'm going to make sure that I save this on the desktop and hit save. And I'll put this in Moodle for you guys as well, so you'll have it if you want to open this up and play around with this circuit and using the oscilloscope as well. All right, so by default, I have a circuit that is 120 volts RMS. 60 hertz is the frequency of this, and 0 degrees. That just means if you have, that doesn't really matter unless you have multiple signal sources. You can actually have them phased differently, like each one starting at a different time from the other one. But the 0 degrees doesn't mean anything if it's just one AC signal source. Now I want to, I'll show you how to use the meter first, just for review. You should know how to do that. So over here on the right, this is my test equipment. And I clicked on the very top one, and that is a meter. And you can see now that the meter icon is attached to my cursor. And I'm going to put it here. And then I'm going to connect one lead to that side of the resistor and my negative lead to that side of the resistor. Then I'm going to double click on it, and I'm going to set it for volts AC. So I have to click the little sine wave symbol there. And now we're going to click the play button here, which is run. Also, the F5 key will run the circuit as well. And you can see that I'm measuring 119.999, or it's really 120. So right at 120 volts RMS. Close enough. And if you don't like it being exactly 120, it could be because our load resistance is a little small. So let's just put in 100K. 100K, and we'll run this again. And that didn't change much, did it? It might go to 120. I'm not sure. It's still showing a little bit of loss in the circuit, but that's okay. Don't worry about that. So I'm going to close that. I'm going to stop the circuit, and I'm going to get rid of the meter. I don't need the meter anymore. All right, so now let's go over here and get it's the third instrument down. No, excuse me, it's the fourth instrument down, and it's called oscilloscope. Right under that, there's another one called 4-channel oscilloscope. So I'm just going to get the one that says oscilloscope. That's a 2-channel oscilloscope. I'm going to put it right there. And I'm going to hook channel A to that point there. Because we're measuring kind of the output of this voltage source. And there's really nowhere else to put it other than if you put channel A here, which that's connected to ground, so you wouldn't get anything there. There is a ground terminal here, a ground lead, and you can connect it there just like we did the meter. Remember, the positive side of the meter was over here and the negative side was there, and that's fine. That will work fine. Just a little hint, a little tip, but in most cases, the negative leads are assumed to be ground in Multisim, and you really don't have to hook those up unless you're in some circuit where it's just not behaving like you think it should, and then you might want to hook those up and see if that makes a difference. So I've hooked it up here just to not create confusion, but it's not really required. In other words, this here would have been just fine. Whoops. All right, moving on. Now let's double click on the oscilloscope, and that will open up the oscilloscope window that you see here. And let's run the circuit. And there we go. And I'm just going to let it sit there and run a minute. Now, over on the oscilloscope, so it doesn't matter whether you're using an old oscilloscope or a new oscilloscope, like the newer digital kind, which we'll look at that in just a moment. Most of the time, the waveform is not going to look properly on the screen because the settings or the adjustments on the oscilloscope have not been customized or set properly for the signal that we're looking at. And so that's the case here. And after you get some experience with oscilloscopes, you'll kind of be able to get a guess of what's going wrong or not right on the screen, and you can make adjustments accordingly. So we've got a couple things going on here. I can see that it looks like this waveform is too large to fit on the screen. So that means the voltage of this waveform is much higher than what I currently have the oscilloscope set for. Now you also have to know a little bit about an oscilloscope is made to measure two parameters. It's fundamentally designed to measure two things. On the horizontal axis, it's going to measure time. In other words, how much time has transpired since this signal began or started. The other thing that the oscilloscope measures, vertically, it measures voltage. So it's a voltage versus time measuring device, and that's it. Now, newer oscilloscopes that are digital and have computerized circuitry will give you more features, and it can actually measure more than just voltage and time. But you take an older oscilloscope that came from the 60s and the 70s and even some of them in the 80s, they can only measure voltage and time. They don't give you all of the other fancy features, so to speak, that you'll find on a modern digital oscilloscope. And that's okay. They all have their uses. All right, so I've already given you a hint that what I'm looking at here on the screen, the waveform is probably too large. So I'm going to go to my channel A, because that's the only thing we're using right now. We hooked up channel A to our voltage output here. And channel A is currently set to 5 volts per division. That means that each one of these vertical divisions, which there's 6 of them, each one of them measures 5 volts. So right now at 5 volts per division, this window or this screen can show plus 15, to negative 15 volts. So above the middle line, we can get up to 15 volts. Again, that would be 5, 10, 15. And then below the line, it would be negative 5, negative 10, negative 15, because remember, it's 5 volts per division. So we already know that we're working with a voltage that's very high. In this case, it says 120 volts RMS. We'll come back to that. So let's begin to adjust our channel A scale, which is our volts per division. And I clicked in there, and now I'm going to select the up button. So now it goes to 10 volts per division. Now we're looking at plus 30 and negative 30. You see the waveform is still way off the screen. There's 20. There's 50. We're getting there. Looks like we got a sine wave here. And there's 100. That looks pretty good. 100 volts per division. So that would be up to 300 volts positive and 300 volts negative if it's 100 volt for each division. And that would mean each square, each vertical square is 100 volts of amplitude. Okay, so now that we've got our channel adjusted pretty good, it looks like that the waveform is kind of dancing across the screen. And that's okay, but I would love to have a waveform that was kind of stationary, almost looking like it's still in a way. And we can do that. The oscilloscope gives us that capability. The adjustment on an oscilloscope that does that is called the trigger. And what the trigger does is you set the trigger level. Well, first of all, you set the trigger type to what do you want to trigger on. Do you want to trigger on an edge, like a rising edge or a falling edge, or something else? And it depends on the oscilloscope and what options you have. In this case, you can see that it is currently set to the rising edge, and that's okay. And I'll show you in a moment how that will change. And the trigger is actually turned off. It has been set to none by default. So what we're going to do is we're going to set it to normal. Now we've set it to normal. And the level has been set to 0 volts. So what that means is on the rising edge at 0 volts, this oscilloscope will trigger or sync the waveform on the left side of the screen at that point. So if you look at the left side of the screen, we have, it's at the left side of the screen, this waveform starts at 0 on the rising edge. So it's 0 volts on the rising edge. So that's where the waveform starts. So let's click the falling edge and leave the level at 0. Now, if you'll notice, the waveform starts at 0 volts on the falling edge. So every time we have a falling edge, it's going to actually sync the waveform at that spot. And what that does is it kind of simulates that the waveform is not dancing around on the screen. Since the waveform, every time the screen refreshes, it's starting at the same point at a cycle, it makes the waveform kind of look like it's standing still. It's really not. Time's still moving on. This waveform is alternating back and forth very quickly, 60 times a second. But it gives us a much more stable display. So that's the purpose of trigger. Again, for most purposes, leaving it on the rising edge will be fine. Now, sometimes the trigger level set on 0 will be fine. Sometimes that will not work. You will have to adjust the trigger level. And let me show you what the trigger level does. Again, that selects the voltage at which this waveform is going to sync on the left-hand side of the screen. So let's change the level to 50 volts. There we go. Now, if you'll look, the waveform on the left side of the screen now starts at the 50 volt mark on the rising edge. So then you'll look, you can see that right there. That's 50 volts on this sine wave. I don't know what the peak voltage is yet, but we can actually go to 100 and click out of it. And now it starts at the 100 volt mark of the waveform, which notice that that particular point is on that exact line of the first division, because we are currently set to 100 volts per division. All right, so that just tells you a little bit about the trigger. You say, well, you know, as long as the waveform is stable, what do I need? Why would I need to change the trigger? You probably don't. But there are times that you would need to change the trigger to get, or just the trigger to get the waveform stationary or steady or stable like it is here. Now, currently, it looks like we're looking at about 6 cycles on the screen. Sometimes that's great. Sometimes you may want to spread this out and only see 1 or 2 cycles on the screen. And that's going to be your horizontal adjustment or your horizontal scale, or more specifically, that's going to be your time per division or the time base adjustment. And you notice here it's labeled time base, which basically determines how fast the oscilloscope is scanning from left to right. Currently, it is set to 10 milliseconds per division, so that would be 10 milliseconds for each horizontal box or block or division. And you can see by playing with this setting that it can spread the waveform out or it can bring it in like a spring. It's not changing the waveform, it's just changing what it looks like on the screen. Because if you go back to our circuit, our waveform is fixed. It's constant. It's not changing. It's 120 volts RMS at 60 hertz all the time. But changing these settings changes the look of the waveform on the oscilloscope. So now we're looking at just a little over 1 cycle there. There's a half cycle. There's 3 cycles, a little bit more than 3 cycles, right? No, 3 cycles exactly. Oh, okay, interesting. So we're going to leave it right here. Okay, so let's make some real measurements of this particular waveform. Now that we're looking at about 1 cycle here, let's go back to 3 cycles. Yeah, let's do that. Now, there's a couple of ways to make some measurements here. One of them is actually using the old-fashioned grid method, which is actually counting the divisions on the screen to make a measurement. And we're going to do that first. We're going to try it that way, and then we'll look at another method. And to do that, we need to get this waveform lined up. We know on the left-hand side that it's going to start at 0 volts on the rising edge. So that's good. That's a perfect place for this waveform to start at. And then we can find the next 0 volt mark on the rising edge, and that would be 1 cycle. So let's count how many divisions it takes for 1 cycle to occur. So starting over here at the left, that would be 1, 2, 3, and not quite 3.5. It looks like maybe 3 1/3 is what it looks like to me. Something like that. Again, you can't get exact measurements when you're dealing with the counting the division type method. So let's do this first, and then we'll see what we come up with, and I'll show you a better way to do this horizontal division counting. So I'm going to say 3.3, or is that 3.4? Well, there would be half. I'm going to say 3.33. 3.33 divisions. That's just a good guess. A good close guess. So 3.33 divisions. All right, how much time is in each division? Well, go look at the time base. The time base is currently set to 5 milliseconds per division. So that means that we have 3.33, keeps going, 3.3333 times 5 milliseconds. So let's bring up the calculator. 3.333333 times 5 milliseconds equals 16.66666666 and continuing milliseconds. So that's what we have calculated, or excuse me, that's what we have measured for our horizontal time, or the time that it takes for one cycle to the time that it takes for one cycle to occur. What is that? There's a definition for that. There's a word that goes along with the time that it takes for one cycle to occur. You be thinking about that. You may know the answer. All right, so I have measured 16.66667, rounding off, milliseconds. So that is the amount of time that it takes for one of these cycles to occur. Now, a better way to measure the period of a waveform is to get this waveform stretched out as much as possible where you can see one complete cycle. You got to be able to see the whole cycle on the screen, and no more, or at least at the minimum. So adjust your time base until we see one cycle. Now see, that's not enough. That's not a complete cycle there. So I went too low. I went to 1 millisecond. So let's go back up. There's 2 milliseconds. Yeah, that's pretty good. That's 2 milliseconds per division. You're going to get probably a more accurate reading at this point. So let's see. So let's count. 1, 2, 3, 4, 5, 6, 7, 8. 8.333333. I think so. Yeah. 8.333333 divisions. So that's 8 blocks and then 0.333, or a third of another block. Each block is worth 2 milliseconds. So it's going to be 8.3333 times 2, which is 16.6666667. So again, we get the same answer, but it looks different on the screen. Okay? So that is 16.666666 milliseconds for the period of this waveform, capital T, the period of the waveform. All right, so that's how we measure the period of the waveform using the old-fashioned. You can use that method on any oscilloscope that has the grid on it. It doesn't matter if it's a brand new one or if it's one that's 50 years old. The old oscilloscopes, they have a time-based control. They have a volts per division control for the channel. And they also have a graticule on the screen. That's what the grid is called. And so you can take the graticule that's on the screen, the settings on your time base, and the settings on your channel on a 50-year-old oscilloscope, and you can come up with what we just came up with. 16.66667 milliseconds for the period. Now, do you remember how to calculate, since this particular oscilloscope does not calculate frequency, and older oscilloscopes don't either, do you remember how to calculate the frequency if we know the period? So real easy formula. So in other words, F, which is the frequency, equals 1 divided by the period. That's an easy one. So you just put in the amount of time that represents the period of the waveform in your calculator, and then you hit the 1 over X key. So it's the inverse. So it's the inverse of time. So 16.666666 hit the 1 over X key, and I get 60 hertz. And don't forget that's in milliseconds. So when you put that in your calculator, you're not entering seconds. Don't put in 16.66666 seconds. It's milliseconds. So you have to convert that to seconds, which is what? 0.0166666666. Or you can put in 16.66667 times 10 to the negative 3. You can do that as well. So whatever method works for you guys on using the calculator, just come up with something that is most comfortable for you on how you enter in milliseconds or microseconds or nanoseconds, how you handle that in the calculator. Some calculators have those features built in where you can directly enter the milli or the micro or nano or a kilo or a mega. But you need to know how to do it without using those, because you may, if you get too comfortable with that calculator, then you won't be able to use another calculator that doesn't have that feature. So you want to be able to do this on any calculator, any scientific calculator, at least. Okay, so now we've taken care of measuring the period, and then now that we know the period, we can easily calculate the frequency. So again, does not matter what oscilloscope you get, you can use that method. All right, I'm going to adjust my time base again to get some more cycles on the screen. The next method can be used on most oscilloscopes that's been made in the last 20, 25 years, or any scope that has cursors. Cursors are these little bars or measuring sticks or whatever you want to call them. They're called cursors. But and all new oscilloscopes have them, and especially all scopes made into, the last few years have them. But they started appearing on scopes in the 90s. I don't know that there may be some from the 80s that had them. I'm sure there were. But they would have been on the real expensive oscilloscopes. Most of them didn't have it. Tektronix is a brand that's been a leader in oscilloscopes forever. And they've had they did a lot of pioneering in the oscilloscope world and had a lot of innovations, and they're still a big name brand when it comes to oscilloscopes. But anyway, cursors. Cursors are an easier way to make measurements in or on the waveform. And I'll show you that. So this particular cursor, we can place it anywhere on this waveform. This is cursor number 1. You can see that there, and it's blue. Here is cursor number 2. It's yellow, and we can move it anywhere on the waveform. And depending on the scope that you have, there are different ways. Now here in Multisim, you can drag these cursors with the mouse. On a real oscilloscope, some of them you enable the cursors, and then you have to use like a little control knob to move the cursors back and forth where you want them. There is some automatic placement of cursors on some oscilloscopes as well. But the basic way to use a cursor is you just manually put it in place in where you want it. Okay? So for instance, let's put this first cursor on this very first peak, which is approximately right there. And let's put the next cursor on the next peak in hopefully the exact same position on the peak, which is approximately right there. Let's go ahead and hit stop. Whoops. Let me hit start again. Oh no, that messed up my daggone cursors. Let's set trigger to auto, and I'll show you why I did that. Setting trigger to auto, then we can hit stop. And what that does is it actually is retaining memory from the whole waveform or the whole time we were just running the circuit. And so I can actually scroll back in time and look at the waveform. That's going to stabilize our display, and we don't have the little flickering going on because the actual circuit was running. Also takes the load off the computer. The fan goes down, or my fan now is finally going back down to idle. But now we can use the cursors. So let's drag over cursor number 2. Let's put it here on the peak. And then let's get cursor number 1 and let's put it on this peak, like so. And then hopefully we've got them center way of the peak at the very highest voltage point on both peaks. Now from peak to peak, or from this tall peak to this tall peak, is considered one cycle. Start there, we go negative down to the negative peak, we come back up, and then the process would repeat again. So that would be one complete cycle. So now the time that's in between these cursors would represent the period of this waveform. Now, if we go down and look at our cursor window, it shows us some information for the first cursor, which is cursor number 1. And then it also shows us information about the second cursor. So the first cursor appears at 4.137 seconds. The second cursor appears at 4.154 seconds. And then what we're most interested in is not that. Don't let that confuse you. That's just showing the absolute time at those two spots. What we're interested in is the difference between these two cursors, and that would be the time between the two cursors. And notice that that is 16.667 milliseconds. Again, that is capital T. That's the period of this waveform. Also, we know from our cursors that our cursors are sitting at 169.031 volts. So that tells me what the positive voltage is at that point, 169.031 volts. And so it is with the second cursor as well. That has nothing to do with the time relationship, but it does show us the peak voltage of this waveform. If I decide to move the second cursor down to the negative peak, notice the second cursor now is at negative 169.031. Again, that's the peak voltage, 169 volts. What is the peak-to-peak voltage? Well, the peak-to-peak voltage now would be the difference between these two cursors. The first cursor is at the positive peak, which is a positive voltage. The second cursor is at the negative peak, which is going to be a negative voltage. And the difference of those two voltages is going to be rather large, and that's the peak-to-peak voltage. And if you go here, you can see that the peak-to-peak voltage is 338.063 volts, or just say 338 volts. Well, where did this 169 come from? I thought we had 120. Well, we do have 120 volts, RMS. Oscilloscopes don't measure RMS voltage, or they kind of do. And I can teach you how to measure RMS voltage on oscilloscope. And we'll do that in just a second, just for fun. How about that? But to convert RMS voltage to peak voltage, or peak to peak, let's just do peak voltage. That's the easier one. RMS to peak, you would divide by 0.707. So going back to my calculator, 120 volts RMS divided by 0.707 equals 169.7. So see there, 169 volts. And since this Multisim is trying to simulate a realistic circuit, and it is, the voltages are not going to be exact because we've got some voltage loss or voltage drop here in the circuit. So we're actually measuring a little bit less than what we're calculating, which is okay, no problem. So we do have 120 volts RMS, but we actually have 169 volts peak, or 338 volts peak to peak. That's a lot of voltage. That's how much voltage you have at your receptacles in your home. Yes, they're 120 volts, but they're 120 volts RMS. So you say, well, I got shocked by 120 volts. No, you got shocked by 169 volts peak, or by 338 volts peak to peak. So you got more than 120 volts. So what is the RMS voltage? Well, it stands for root mean square, and it's very close to like the average voltage. It's not really the average, but it's close. So you can see that the voltage is constantly changing. It's going from 169 back to 0, and then the negative 169 back to 0, and then 169 and back to 0. And it's doing this 60 times a second, over and over and over and over. But so it's never constantly at one particular voltage. The voltage is really moving around. It's fluctuating, or it's alternating between positive 169 and negative 169. But the average, or what they call the root mean square, is 120 volts. And I'll show you where that comes from. That, at least for a sine wave, that's very easy to determine. You also have to know that on a sine wave represents 360 degrees of rotation, or 360 degrees in a circle. So let's get rid of the cursors. Oh, one other thing. If you right click on these cursors, you can automatically position them. So you can set the cursor to go to a maximum value or a minimum value on the waveform. Or you can set it to go to a certain value. So that's a little trick that you can do for the cursors. Or you can just do like I did, where you just manually move them where you want them, and then you read the data here in the window, either way. All right, so let's get rid of the cursors. Let's move them back over to the left where they just hang out when they're not being used. And let's see. How are we going to demonstrate this? Let's run the circuit again. There we go. And let's go back to normal trigger, like so. So now the circuit is running, and we are starting at 0 here on the left. And let's show one cycle on the screen. There we go. All right, so now let's grab a cursor and let's bring it over. Let's just get 2 over here out of the way. Let's bring cursor number 1, and let's try snapping this to the peak. So right click, go to next Y max. There we go. Well, that doesn't look like it's in the right place, but I'm going to manually move that a little bit. Okay, so as you can see, we have put the cursor on that peak, and actually it probably is a little bit further than that, to be honest. It probably put it in the right place, to be honest. Why am I second guessing the computer, right? Like so. That might be right. Well, let's go with it. So if you know the different parts of a sine wave, and that one complete cycle on a sine wave represents 360 degrees in the circle, then you also know that when you start out on the sine wave, which we did here, that's 0 degrees. And then when you get to the halfway point of the cycle, that's 180 degrees. That's where the voltage is again 0 volts. What is this angular measurement at the first peak, or at the positive peak? Well, that's 90 degrees. And then if you go to the negative peak, that's 90, that's 180, that's 270 degrees at that peak, the negative peak. And then if you get back to the 0 mark again, you're now at 360 degrees. You've made one complete rotation on the circle. You've completed one cycle of the sine wave. Also, you have to know a little bit of math. Not much. It's just the sine function. The sine function is but once you learn it and once you know it, which is very easy, it's not hard, and you can visualize it on the screen. The sine function says that, at least from practical standpoint, that the sine function at any angular measurement here in the cycle gives us the voltage amplitude at that particular measurement. So in other words, you said this was 90 degrees. So what's the sine of 90 degrees? Well, we'd have to pull up our calculator. We put in 90 and then hit the sine button, and you should get 1. So the answer is 1. The sine of 90 degrees is 1. And if you want to convert that to a percentage, you can. But what that says, it's 1 times the maximum voltage of that particular waveform. In our case, the maximum voltage of this waveform is 169. So at 90 degrees, the voltage is 169. It's 1, or 100%. Okay? Let's move on. What is the voltage here? Well, I can look at it and tell you it's 0. But what's the angular measurement there? Well, the angular measurement halfway of the cycle is 180 degrees. That's halfway around the circle. Well, what's the sine of 180? It's 0. So it's 0 times the maximum voltage, which is what? 0 times 169 volts is 0 volts. So there's no voltage at the 180 degree mark. What about 270 degrees? What do you think the sine of 270 is? Put 270 in your calculator and hit the sine key. I guarantee you it's -1. Look at there, -1 times the maximum voltage. Maximum voltage is 169, so that would be -169. And then finally, 360 degrees. We've made it all the way around the circle, and we've come back to 360 degrees, which is really kind of the same spot as 0. So what do you think the sine of 0 is and the sine of 360? Try it in your calculator. The answer to both is 0. Now, let's make up something realistic. Now, we've done the easy ones. We've done the 90, the 180, the 270, and the 360. But what if I pick just some spot on the side, like during the rotation of the circle, I just randomly say, okay, how about 50? How about 50 degrees? What's the sine of 50? Well, you have to put that in your calculator. It's going to be somewhere between 0 and 1, or 0 and -1. I can give you a guesstimation of what it is by looking at the sine wave. I know that anything between 0 degrees and 90 degrees has to be between 0 and 1. See that? Can't be a negative number because we're not into the negative portion of the voltage measurements here. Anything after 90 degrees, from 90 to 180, is also going to be a positive number. So as we leave 90, which is 1, and we start getting closer to 180, the sine values are going down. So we're going from 1 to 0.9 to 0.8 to 0.7, 0.6, 0.5, 0.4, 0.3, 0.2, 0.1, until we get to 0 back at 180 degrees. So what do you think the sine value of 181 is? Well, I don't know, but I do know it's negative, because anything after 180, notice what the waveform is doing. It's going more negative. So it's going more negative until it gets to a maximum of -1 at 270. And then 271, 272, as you begin to approach 360, the negative values are getting back closer to 0. So that's all the sine function is. The sine function is telling you what the voltage is at some spot in that circle, some angular measurement in the circle. So now, what's all that got to do with RMS? Well, RMS is easy. RMS is the voltage that's halfway between 0 and 90 degrees. Or it's the voltage that's halfway between 90 degrees and 180 degrees. Or it's the absolute voltage measurement of halfway between 180 and 270. Or halfway between 270 and 360. So let's go back and make it easy. Let's go back to the 90. I'm going to spread this out just a little further because we don't need to see the whole cycle since we're only working with, and that would do there. That might be, let's just do this one. I like this one better. So now I'm just looking at a little bit more than half the cycle. Starts at 0. Here is the 90 degree mark. So all I have to do now is basically find the 45 degrees, because what's half of 90? It's 45. So it's the 45 degree mark on the sine wave. This would be easier to see on a circle. Think of a circle, a pie, and you cut 4 pieces, or think of a pizza. You cut a pizza into equal 4 pieces. Each piece of pizza represents 25% of the circle. Okay? That means that each side of the pizza that you just cut is 90 degrees. It creates a 90 degree angle. In other words, it's like the 4 quadrants. You get what I'm saying on the pizza. The 45 degrees would be half of that. So the RMS value is the voltage that occurs halfway between 0 and 90 degrees, which is 45. So we would need to put our cursor at 45 degrees, which is halfway between 0 and 90. I don't know exactly. I'm just eyeballing it here, to be honest with you. But we could actually measure the time. We'd have to find out how much time is in 90 degrees, which will be, what, a fourth of the period. Remember, the period was the time that it took the whole cycle to occur, which we said was, what, 16.666? 16.66667 milliseconds divided by 4 equals, I got 4.1666667. So 4.1666667 is the time in 90 degrees, or that's 25% of the entire period. And I hope I'm not confusing you. And if I am, you can rewind and you can go over it to get a little bit of grasp on this. So what I'm having to do here is find half of 4.16666. So I divide that by 2. That gives me basically 2.1. We're just going to round it off to 2.1 milliseconds. So at 1 millisecond per division, I go over 2 divisions, just a little bit more. And that's where I've put the cursor. Okay. Can I hit stop? Yeah, I can hit stop. That keeps all these values from dancing around. So what that tells me is, and this is not a precise, what I've done is not precise, not really, but it's just giving you a ballpark. So the cursor is sitting at about the 45 degree mark on the sine wave. And if you look at the voltage at cursor number 2, because that's halfway. Remember, cursor number 1 is, I don't have it in exactly the right spot. It should be 169. 169.3, 0.4, something like that. Okay. So this is a little low. So somewhere in there would be about halfway. So in other words, I'm trying to get the yellow cursor halfway between 0 over here on the left and the blue cursor. And And right now I'm just eyeballing it. It could be a little low too, but that's close. Now notice it says my voltage is 123. Again, for this is a little unprecise. That's pretty good. So the RMS voltage occurs halfway between 0 degrees and 90 degrees, and which I'm measuring about 123. Should be 120, but again, it's close enough for doing it using this method. So that gives you a little idea on how to find the RMS voltage on an oscilloscope when you don't have a meter or you don't have any way to determine that other than using the scope itself, especially if it's an older scope. And this only works with sinusoidal waveforms. In other words, waveforms that are pure sine waves. You can do that. And so that's a little bit about how to measure RMS voltage on an oscilloscope. So far we've been able to measure period. We've been able to measure voltage, peak-to-peak voltage, and then we've just measured RMS voltage on an oscilloscope using nothing but cursors. All right, moving on quickly. Let's start the circuit back up, and let's get our oscilloscope back to showing some cycles here, like so. We currently have our trigger in normal mode. We can put it in auto. Again, if you want to rewind the waveform, you'd have to have it in auto mode. Normal mode looks good if you just want to view it, make some measurements while the circuit is running. It works really great for that. The negative side of normal mode is when you stop the circuit, sometimes the waveform will disappear. Sometimes it'll only just show a little portion of it. It depends on where you stop the circuit at. It's going to stop right at the point that it was drawing the waveform on the screen. And notice I can't back up. I can't do anything. If we were in auto mode and did the same thing, the waveform doesn't look good. It's not stable on the screen, but I can hit stop, and then I get this little scroll where I can actually scroll back and get the waveform on the screen just like I want it. So that's a little trick in using auto or normal for your trigger. Okay. Let's see other things. Other things about this oscilloscope window would be, again, it's a 2-channel, and if you're looking at 2 waveforms, so let me hook up channel B. I'm going to hook up channel B to channel A. So channel A and B are measuring the same thing. Now, usually you're not measuring the same thing with both channels. That really doesn't make a lot of sense, but just demonstrating. Now you can see there's 2 waveforms on the screen, and I'm going to adjust. So now it looks like there's only one on the screen, but there's actually 2. One's on top of the other. To get the screen where you can see both of them, you can superimpose waveforms over top of each other if you need to. That works good in some instances. Sometimes you want one of the waveforms on the top of the screen and one toward the bottom. And to do that, you use the Y position here, and we can move channel 1 up, and we can move channel 2 down by adjusting the Y position. So now you can see we're looking at both channels simultaneously. One's on the upper part of the screen and one's at the bottom. This is really handy if you're wanting to compare the 2 waveforms with each other time-wise. Works really good for that. To see, like now you could bring a cursor over, for example, and you could see if both of these waveforms are in sync or if one is just a little bit ahead of the other, that type of thing. If you want to compare voltages of the 2, it might be best to have both of the waveforms one on top of the other, like we did earlier when we had the Y position set to 0. So that's the purpose of the Y position adjustment. This is also true on a real oscilloscope. You'll have a Y position adjustment. You'll also have an X position adjustment where you can actually move the waveforms left and right. See that? Again, that's for making measurements. Getting them lined up with the graticule or the grid so that you can make a precise manual measurement. So I just wanted to point those out. Let's get rid of channel 2. We don't need it really. There. One other thing, the color of the waveform, in this case it's red. The color of the waveform will always match the lead color. So if you want the color of the waveform to change, like if you have two waveforms and you want one of them to be one color and one another color, change the lead color. And to do that, just select it and then right click on it and go to segment color. And we can change that to yellow. It's hard to see the lead on the screen, but now the waveform will be yellow. So the waveform will always match the lead color or the wire color to the oscilloscope. So I hope that has been helpful in using the basic oscilloscope here. In the next video, I'm going to show you the same things that we've done. It'll be obviously much more consolidated because I won't have to go into much detail. But we're going to use the Tektronix oscilloscope to make some measurements too. It has more features. It's a little bit harder to operate, but you'll get to see it done both ways. So I hope that helps. This should be on the way to doing the upcoming labs of using the oscilloscope. So this gives you a pretty good primer. Sorry I went off on a huge tangent on the RMS voltage, but it's really cool when you start to grasp that it's not really that complicated. A lot of this stuff can seem really complicated in the beginning, you know, the sine and the 90 degrees and the 180 degrees, but eventually it all starts coming around. At least I hope it does. I'd love to get some feedback from you guys on what you think. Is there a way I can explain it better for you? I'd love to know if you're learning, if you're grasping this stuff any better. So give me some feedback on that, and let's start the next video right now on using the Tektronix oscilloscope in Multisim.